Hey guys, this is Professor Janacek, and I want to talk about related rates. Now these will come in the form of word problems, so let's go over a procedure that will help us solve them. We'll begin by sketching a picture to help us describe the situation, then we'll identify the known values as well as the unknown values. We'll want to then write an equation that relates all of these quantities together, and then we'll differentiate, and that will be with respect to time. Next, we'll evaluate, and finally, we'll solve for the unknown. We do want to make sure that we evaluate at the end and don't evaluate too soon, or that could cause major problems. Let's take a look at the first example here. We have an oil rig that springs a leak in calm seas, and the oil spreads in a circular patch around the rig. If the radius of the oil patch increases at a rate of 30 meters per hour, how fast is the area of the patch increasing when the patch has a radius of 100 meters? All right, well, let's go ahead and start with our sketch. We are looking at a circular patch. So let's draw something circular. Okay, that's supposed to be a circle. Okay. We do know, of course, where the radius can be identified. All right, so what are we looking at? So just to be aware, we are trying to determine the area of this patch when the radius is increasing at 100, when the radius is 100 meters, right? So that's what we're looking at. We're looking at area. So let's go ahead and write out. So area and radius are unknowns. We want to kind of relate these. Of course, we do know that the area of a circle is pi r squared. I'm going to go ahead and, as a reminder that these are functions of time, I'm going to write them as functions. So a of t is equal to pi times the radius, which is also going to be changing with respect to time. Of course, that radius is squared. Now, in practice, of course, we will consider this as a is equal to pi r squared. I just wanted to remind myself that both area and the radius are changing with respect to time. Now let's see. Since the radius is a function of time, we can actually write this one out as well. We see that our radius increases at 30 meters per hour. So we can write this as 30t. So for every hour, it's going to increase 30 meters. Do notice that this is meters per hour. And so that means the area of this would be meters squared per hour. All right, well, I think that gives us a lot of what we need. Here with this radius equation, I will write it as r is equal to simply 30t. All right, so now we have our knowns and our unknowns. We know we have an equation that relates them. And remember, we are specifically looking at area, and so this is going to be my main equation. All right, we're ready to differentiate. A prime is 2 pi r. Remember, we do need the chain rule, so that gives us r prime. Following that r. Don't forget how to use that chain rule here. And looking at this, it seems that I'm going to also need to know what r prime is. Well, if r is 30t, then r prime is simply 30. Remember, we're differentiating with respect to time, so I do not need to write t prime. T prime is just 1. And so that takes us back here and allows us to write a prime as 2 pi r times 30, which of course gives us 60 pi r. Now here's where we're going to go back and use our radius is 100 meters. So that gives us that A prime, the area, is changing at a rate of 60 times pi times 100, which is 6,000 pi. Thus, the area is increasing at 6,000 pi meters squared per hour. All right, let's also take a look at example 2, a water heater that has the shape of a right circular cylinder with a radius of 1 foot and a height of 4 feet is being drained. How fast is the water draining out of the tank in cubic feet per minute if the water level is dropping at 6 inches per minute? All right, so let's begin by sketching a picture of what we're looking at, a right circular cylinder. And we of course know the radius is there, and of course the height will be here. It is filled with water, so let me just go ahead and identify, there's the water level. All right, and what are we looking for? We're looking at the instantaneous rate of change of, well, it says how fast is the water draining out of the tank? Well, what that means is we're looking at the instantaneous rate of change of the volume. So we're going to have to come up with an equation for the volume. Notice in example 1, it told us the area. That was already kind of given to us, so we didn't have to kind of think through what it is. In this case, it doesn't actually say volume, but that is what we're looking at. All right, well, we'll need an equation for this volume. We know that volume is pi r squared h, volume of a right circular cylinder, pi r squared h. Now I want you to notice that my radius never changes. We do know that the radius is 1, and initially the height is 4 feet, but this height is changing. It is changing, it is dropping at 6 inches per minute. That is a change in the height. So that height is also changing, so that means I'm going to have to write the height as a function as well. So we can simplify this just a bit. We know that the radius is 1. That does not change. So that gives us that V is pi h. Now, again, h is a function, so let's see. Let's take a look at that. We know that this is, oh dear, this is 6 inches per minute. But notice we want our result to be in feet per minute, cubic feet per minute to be exact. So I need to make sure to change this 6 inches per minute. Well, that's 6 inches over 1 minute. We know there are 12 inches per foot. So this reduces to 1 foot per 2 minutes. So our height is changing at 1/2 foot per minute over the time. So our height can be written as 1/2 t. Make sure you understand that this is now in feet per minute. So our volume will then be in feet cubed per minute. Okay, well, I think it's time for us to differentiate. V is equal to pi h, so V prime would be pi h prime. Well, that means I'm going to need to figure out what h prime is. H is 1/2 t, so h prime is simply 1/2. That gives us pi times 1/2, or pi over 2 for the volume. Now, we're looking at, oh, nope, and that's it. We've got it all. We figured everything we needed. So therefore, we see that the volume is decreasing in this case at pi over 2 cubic feet per minute, or feet cubed per minute. And there we go. Enjoy!